Good morning. Hi everybody. I am Vempati Srinivasulu, Assistant Professor of Chemistry, working at Nagarjuna Government Degree College, Nalgonda. This lecture is meant for BSc second year chemistry students, third semester. Okay. So we have been discussing about coordination compounds. So far what we have discussed. What are coordination compounds? What are double salts? How coordination compounds differ from double salts? What are the examples for coordination compounds? Then, what terms involving in coordination compounds? Complex ion, central metal atom or ion, ligands, cationic complex, anionic complex, coordination number, chelating ligand. All these terms discussed, defined with examples. Then we discussed IUPAC nomenclature of coordination compounds. So we have by taking different examples, by using this IUPAC set of rules, we have been given two different names to different compounds. And also, if you know the name, write the formula. If you know the formula, how to write the name. We have discussed this IUPAC naming method. Then we discussed Werner theory of coordination compounds. This theory is explained by taking four examples: cobalt chloride complex, ammonia, cobalt, hexamine, cobalt chloride examples. Then we discussed demerits of this theory, followed by we discuss electronic rule, that means Sidgwick rule of electronic interpretation, that is nothing but effective atomic number. We calculated different complexes effective atomic number of different metal ion complexes. So what is effective atomic number? How some compounds are stable, how some are unstable, and how to calculate effective atomic number. This discussed in the previous classes. Then what are the limitations of EAN? We can't explain with this EAN all stability of all complexes. Okay. Then okay. The previous class we have discussed. We have started theories, coordination theories. We have different coordination. There are some theories which explains this coordination compounds properties, structure. One is a valency bond theory. A second one is a hybridization, molecular hybridization theory, MOT, and a CFT, crystal field theory. So we have started in the last class valency bond theory. This is the recap what we have discussed up to now. So today class, what is a VBT? We have discussed in the previous class. This theory is applied to tetrahedral complexes in the previous class. Today we will discuss this valency bond theory to square planar complexes and octahedral complexes. So we'll discuss these complexes. Then we're going to start the sim off, otherwise phone will come. Okay. Then, so in the valency bond theory, just we discussed something about valency bond theory. What are the postulates? So as per valency bond theory, central metal atom or ion has to provide required number of vacant orbitals. This required number of vacant orbitals depending upon coordination number of a particular complex. This is the first point. Second point is these orbitals undergo hybridization, mixing of these orbitals to give new and equal energetic hybrid orbitals. That means second point tells us before taking part in bond formation, the orbitals undergo hybridization. Third point, if the d orbitals involved depending upon two complexes, two inner orbital complex, outer orbital complex. If the d orbital n-1 d orbital is involved in hybridization, we call that complex is inner orbital complex. Whereas nd orbital is involved, we call those complex as outer orbital complex. Okay. Then these hybrid orbitals hybridization decides the geometry of complex. Then the ligand which should have at least one electron pair, lone electron pair on an atom of a group, it is capable of donating this electron pair to the central metal atom to form a coordination bond. That means ligand should have an electron pair and an atom that should be available for donation. Ligand. Then last point is these filled orbitals of ligands overlaps with vacant orbitals of hybrid orbitals of metal atom, leads to formation of coordination bond, ligand to metal bond, metal ligand bond formation takes place. These are the different important postulates of valency bond theory. Then we discussed in the last class this theory is applied to tetrahedral complexes. So now in this class we'll discuss, okay, you see, square planar complexes. First we apply this theory to square. For example, nickel tetracyanidonickelate 2 is one complex. So the tetracyanidonickelate 2. So what is how we explain the geometry and magnetic behavior of this complex by using valency bond theory? Let us see. So this nickel tetracyanidonickelate 2. It means it is a anionic complex. Minus charge is there in the complex. There is an anionic complex. In this anionic complex, nickel is the central atom. Okay. It is linked, it is bonded to 4 cyanide ions, that is ligands. That means it is the coordination number of nickel plus 2 is 4 in this complex. Okay, that means nickel has to provide 4 orbitals. So let us see, in the nickel is in 0 state. What is the nickel atomic number? 28. The outer electronic combination is argon 4s2 3d8. We know that. So this is a what is this? This is a ground state electronic configuration of nickel with 0 oxygen state. But in the complex, it is exhibiting plus 2 oxygen state. Its primary valence is 2 plus 2. That's why it has to lose 2 electrons. Yeah, that means nickel plus 2. So these 4 electrons lost. So due to this nickel plus 2 state, this is a 3d8 4s0 4p0. This is the electronic configuration. So in this situation, okay, it is having 2 unpaired electrons. But what happens in the excited state? This electron pairs up in the 3d orbital. So in this pairing, due to this pairing, we are getting one vacant d orbital. So already I told you, nickel in this complex, nickel has to bond 4 coordinate bonds with 4 ligands, 4 cyanide ligands. So that's why one d orbital and one s orbital and 3 p orbitals intermixing. No, we require only how many? 4 orbitals. So one s orbital, one d orbital, and only 2, not 3. sp2, one d orbital and one s orbital, 4s orbital, and 2 4p orbitals intermixes to give equivalent dsp2 hybridized orbital. We know dsp2 hybridized orbitals arranges in a square planar geometry. So at the center of the geometry, we have nickel atom, nickel ion, Ni plus 2. So these vacant hybrid orbitals overlaps with 4 cyanide. That means these orbitals are accepting electrons from ligands. That means we have shown these electrons in this dotted line. So this is 4 dsp2 orbitals are accepting electrons. That means filled orbitals of cyanide ligands, 4 ligands, is interacting with vacant hybridized dsp2 orbitals of nickel ion, nickel plus 2. So due to this, there is a 4 coordination bonds taking place. This is due to this dsp2 hybridization, this compound, this complex is exhibiting square planar geometry. Further, we can, as per practical values, practical observation, this compound is exhibiting diamagnetic property. This is explained by all paired electrons. There is no unpaired electron in the d electron. So generally, d black elements are coordination compounds exhibit magnetic behavior, paramagnetic or ferromagnetic property due to availability of unpaired electrons in d orbital. We know that. So since it is lacking d unpaired electrons in d orbital, that's why this is a diamagnetic compound. So this is a explanation through valency bond theory to this tetracyanidoniculate 2. Okay. So this is the shape of the complex, you see. So this is a complex, you see. In this complex, nickel ion is at center of the molecule. Then it is bonded with the 4 ions. Nickel plus 2 is exhibiting as dsp2 hybridization. It is a diamagnetic in nature. The geometry shape is the shape of the molecule is square planar. So the last class we discussed 4 coordination number. This may be this exhibit either a tetrahedron or square planar. So this complex is exhibiting square planar complex due to dsp2 hybridization. Okay, then next slide. Okay, one more example. Okay, this one is over 2, okay, 3. All right. So one more example for square planar complex is a tetraamine copper 2 ion. You see the name of the compound. This is a complex. We are studying about this complex. So we are discussing VBT theory. We are applying VBT theory, VBT to square planar complexes. Okay, this is one more example. What the name of the compound complex is? Tetraamine copper 2 ion. It is a cationic complex. In this complex, copper is the central metal ion. It is coordinated to 4 amine ligands for ammonia molecules. Ammonia is a ligand. Amine, we use amine. So this is the name of the compound, tetraamine copper 2. Okay, so how will we explain this geometry of this complex by using valency bond theory? You see, first copper in the 0 state, central atom is copper ion, copper atom, copper ion. In the copper 0 state, you know, copper atomic number of the copper is 29. The electronic configuration is 4s2 3d9. We know that. Okay. Actually 4s2 3d9. Actually 4s1 3d10. Okay. Then in the plus 2 state, it lost 2 electrons from this s orbital. So due to that, or we can say this one also 4s1 3d10, 1 electron from 4s and 1 electron from d. So this is the electronic configuration of copper in plus 2 state. So in the excited state, okay, this electron is moving from here to here, p orbital. So in this excited state, d orbital is available for hybridization. 1 d orbital, 1s orbital and 2 p orbitals mixing or undergoing hybridization. After hybridization, we are getting 4 dsp2 orbitals. So these are the 4 dsp2 orbitals. So these 2 dsp2 orbitals or so this one 1 2 3 4. Okay, 1 2 3 4. This is a one unpaired electron. It is not involving the bond for hybridization. So due to dsp2 hybridization, we know that dsp2 hybridals arranges in square planar geometry in the center of the molecule. The copper is occupying at the center. This copper is having 4 dsp2 hybridals. These 4 dsp2 hybridals are overlapping with 4 amine ligands, 4 ligands, by forming coordination bond, ligand to metal bond. So due to this, this complex is exhibiting square planar geometry. Okay. Okay. This is about what? Tetraamino copper. So we take one more example. You see, tetrachloridoplatinate 2 ion. One more example for square planar complex. You see, this is a complex. Third example. The name of the complex is tetrachloridoplatinate 2 ion. Why platinate? Since it is bearing negative charge on the complex, that's why it is tetrachloridoplatinate 2 ion. So in this complex ion, central metal atom is platinum plus 2 ion. In the platinum 0, we know platinum is coming to nickel group, nickel, palladium, platinum. So nickel is 28, that's why 4s2 3d8, 6s2 5d8 is the electronic configuration of platinum in 0 oxygen state, in atomic state. Whereas in the platinum in plus 2 oxygen state, it loses 2 electrons from 6s orbital. That's why it is a 6s0, 6p0 and 5d8. These electrons, 5d electrons pairing in the excited state. Due to pairing, it is a one d orbital is available as vacant orbital. So mixing of this d orbital, 5d orbital, 1 6s orbital and 2p orbitals, we are getting d2 dsp2 hybridized orbital. It also inner orbital complex. Why? Because 5d is involving in the hybridization, not 6d. Okay, and mass 1d is involving. So due to this hybridization, 4 dsp2 hybridals interact with 4 filled orbitals of 4 chlorides. Due to this overlapping, due to this electronic transformation from chloride to metal ion, there are 4 bonds takes place. So due to this, tetrachloridoplatinate 2 ion exhibits square planar geometry and diamagnetic in nature. Due to non-availability of unpaired electron in d orbital, this compound exhibits diamagnetism, diamagnetic property. This is also proved experimentally. Its compound is diamagnetic in nature. Okay, then 5. Four is over. Okay, this compound is over. So this pairing is taking place. It is against to Hund's rule. This theory that doesn't explain this pairing. So we'll take one more example. Okay, these we discussed so far. Different square planar complexes in which central metal atom or ion is involving dsp2 hybridization. Now we'll discuss octahedral orbitals, octahedral molecules. A coordination with 6, coordination number with 4, the compound may exhibit tetrahedral or square planar geometry depending upon the hybridization. In 6 coordination compounds, generally we see octahedral geometry. Okay, for example, if you are taking what this compound name, you see, simply you see, okay, this is a compound, complex ion. It's an anionic complex. Why? It's having -4 charge. It's an anionic complex. Then The name of the complex is hexacyanatoferrate 2 ion. Ferrate, it means it is an anionic complex. Iron, you use the ferrum. Ferrate, 2 is the oxygen state of iron, it is a primary valency. In this complex, iron is exhibiting +2 as a primary valency and 6 as a secondary valency, that means coordination number. So we'll explain what the geometry of the complex is, why it is octahedral. You see, is the iron 0 state, iron atomic number is 26, we know that 4s2 3d6, 4s2 3d6 is the electronic configuration of iron in 0 state. Okay, then nickel, it is exhibiting +2 state. The primary valence is +2. That's why it is losing 2 electrons in the formation of this complex from 4s orbital. That's why in +2 state, it is exhibiting this type of electronic configuration. While this 4s0, 4p0, and 3d6. In this case, it is only 4 orbitals available, 4 vacant orbitals. 1 4s orbital, 3 4p orbitals are available as vacant, but we need 6 orbitals. How in this complex is iron is linked to 6 cyanide ligands with coordination bond, so it is requires 2 more orbitals. That's why what happens, the pairing in the excited state of iron 2, these electrons pairs, this electron goes to here, this electron goes to here. Due to this pairing, we are getting this type of electronic configuration, 3d6, 4s0, 4p0. In this state, we have 2 vacant orbitals for hybridization. These 2 orbitals and 1 s orbital and 3 p orbitals mixing. Due to this intermixing of these 6 orbitals, 2 d orbitals, 1 s orbital and 3 p orbitals, we are getting d2sp3 hybridized 6 orbitals. So before hybridization 6 orbitals, after hybridization you are getting 6 orbitals. The difference is equal energy. D orbital, s orbital, p orbitals are having different energy before hybridization. So due to hybridization, you are getting new 6 equivalent energetic sp3d2 orbitals. So these are the 6 orbitals. So these are vacant. So now, and that means as per valency band theory, central metal atom or ion has to provide required number of vacant orbitals. This is one of the point. So these d2sp3 hybridized orbitals overlaps with filled orbitals, electron pair ligands with a lone pair of electrons. That means cyanidoligands. So this filled orbitals of cyanide ligands is overlapping with these 6 d2sp3 hybridized orbitals. So there is a formation of 6 coordination bonds from 6 cyanide ligands to iron ion Fe+2. So this is why, that's why we call this complex is the inner orbital complex. Why inner orbital complex? In this hybridization, n-1d orbital is participating, involving in the hybridization. So 3d and 4d, we are using only 3d, not 4d. So 4s2, 4p and 5d, 3d. So 3d orbitals are involving in this hybridization. That's why we say we classify this complex as the inner orbital complex. So these 6 d2sp3 orbitals overlaps with the filled orbitals of ligands. Due to this interaction of vacant orbitals and filled orbitals, there is a bond formation takes place from ligand to metal. So electron pair shifts from ligand to metal. Due to this, 6 coordination bonds forms. Due to this complex exhibits what? Octahedral geometry. We know in d2sp3 hybridization, all 6 d2sp3 hybrid orbitals occupies all corners of octahedron shape. At the center of this octahedron, iron Fe+2 occupies. So due to this type of geometry, this compound exhibits octahedral geometry. Further, as per experimental values, it is a diamagnetic in nature. It is also approved by theoretically also Since there are no vacant unpaired electrons in the d orbital, that's why this is not exhibiting any magnetic, that means diamagnetic, paramagnetic property. That's why it is diamagnetic. So we are explaining uh, two things. One is geometry and another is the magnetic behavior of this complex. So once again, tetracyanidoferrate 2 complex. Iron is a central atom, central ion. It is exhibiting D2sp3 hybridization. It is an inner orbital complex. It is exhibiting octahedral shape. It is diamagnetic in nature. So all these things we are explaining by using what? Valency bond theory. Okay. Then, so this is one example. We will shift to other example. Okay. So one more example. You see, hexacyanidoferrate 2. Hexacyanidoferrate 2. Okay. This is one example. Hexacyanidoferrate not 2, 3. Before one is Fe plus 2. This one is ferrous Fe plus 3. Both are cyanide ions only, ligands only, but the oxygen state is changed. Okay. So iron is min plus this state. Okay. This is one more example. So for this complex, the central metal ion is iron. Iron in the zero state, it is having atomic number 26. In zero state, it is having 3d 6, 4s2 and 4p0. This is not 4d, it's a 4p. It's a 4p. Then what happens? In the plus 3 state, it has to lose 3 electrons, 4s electrons 2 and 1 d electron. This losing of these electrons, iron in plus 3 state, it is having 3d5, 4s0, 4p0 electronic configuration. In this state, we have only 4 vacant orbitals. 1 4s orbital and 3 4p orbitals. 4d also there, but in 3d complex, in 3d orbital we have single occupied electrons of field. So after in excited state, the pairing up taking place to make available 2 3d orbitals for hybridization. So after pairing, this electron going to this one, this electron going to this one. That's why you are getting 2 pairs, 1 unpaired electron. So due to this, you see, this is a electronic conversion in the excited state of iron plus 3 in this complex. So in this state, it is a 2 d orbitals, 2 3d orbitals and 1 4s orbital and 3 4p orbitals intermixes to give 6 sp3 d2 sp3 orbitals. This is also d2 sp3. That's why this complex is known as inner orbital complex. Why inner orbital complex? In this hybridization, n-1 d orbitals are involving in the hybridization, since it is called inner orbital complex. Due to this hybridization, 6 energetically equal d2 sp3 orbitals forms. These d2 sp3 orbitals, we know that it has octahedral geometry. At the center, iron plus 3 ion occupies. Around this iron plus 3, there are 6 corners in the octahedral shape. So these d2 sp3 orbitals of vacant, which are vacant, these vacant d2 sp3 orbitals overlaps with the filled orbitals of ligands. In this case, we have cyanide ligands, cyanido. In the name, cyanide ligands. So due to this overlapping of filled orbitals of cyanide ligands and vacant d2 sp3 orbitals of iron plus 2, there are 6 bonds formation takes place. This is a coordination number. That's why we are calling this 6 coordination number is 6. So number of secondary valencies is nothing but coordination number of that complex in coordination compounds. Then So this 6 orbitals gains 6 electrons from this 6 ligands. Due to this hybridization, this complex is exhibiting octahedral shape. It is an inner orbital complex. It is diamagnetic in nature. Why? Experimentally, it is proved that it is a diamagnetic. Theoretically, you can explain this diamagnetic nature of this. Paramagnetic nature. This compound exhibits paramagnetic behavior. This reason for this paramagnetic is one electron is available in 3D orbital. So unpaired electrons in d orbitals are responsible for paramagnetic nature. That's why this complex is paramagnetic, not diamagnetic. It's a paramagnetic. So this is proved experimentally as well. This is the valency bond theory application to this complex. Once again, hexacyanide III anionic ion is an anionic complex. In this complex, iron exhibits a D2sp3 hybridization. It is exhibiting 6 coordination number. The D2sp3 hybrid orbitals overlaps with the 6 filled orbitals of 6 different ligands. All are cyanides only, different 6 cyanide ligands. So there is 6 coordination number, 6 coordination bonds taking place between iron plus 3 and 6 cyanide ligands. So this due to one electron available in the 3D orbital, due to unpaired electron, it shows some paramagnetic behavior. So this is a valency bond theory application or description about the geometry and the magnetic property of this complex. So in this complex, iron plus 2 exhibits D2sp3 hybridization. It is inner orbital complex. It is having octahedral geometry. It is paramagnetic in behavior. So all these things we are explaining by using what? Valency bond theory. Next we are going to next slide. So you see that this is the shape of the molecule. You see, this is the shape of the molecule. It is an octahedral shape. Iron is central metal Fe3 plus Fe plus 3. So this is bonded to 6 ligands. This is octahedral. We add this, we'll get an octahedral shape. Okay. Then it's a diamagnetic, but it's a paramagnetic in nature. Then next slide. Okay, one more example. What is this? Hexafluoridoferrate 2 ion formed by this one. You see, this is a hexafluoridoferrate 2 ion. Ferrate, it is a anionic complex. In this anionic complex, central metal atom is iron in +2 state, iron metal ion. It is this called two valencies. Primary valence is 2 and secondary valence is 6. That means 6 coordination number. As per valency bond theory, central metal atom, that is iron ion Fe plus 2, has to provide 6 vacant orbitals for bond formation with 6 ligands. This is the primary issue. Then what is the iron electronic configuration? We will see. Oh, just so I don't know why it's gone. No. Okay. Then. Okay. See, central metal atom is iron in +2 oxygen state. Iron in 0 state is 4s2. You see, 4s2 3d6. You know that 26. So in +2 state, it is losing these 4 electrons. Due to losing these electrons, we are getting 4s0 and this one, 4s0 and 3d6. Then what happens in the presence of fluoride ligands? Electron pairing doesn't happen. This s orbital means you see this 1s 4s orbital, 3 4p orbitals and 2 4d orbitals are involving in hybridization. Due to this hybridization, we are getting sp3d2 hybridized 6 orbitals. You see, these are the sp3d2 orbitals. 1 s orbital, 3 p orbitals, 2 d orbitals. Due to this sp3d2 hybridization, 6 sp3d2 orbitals are available for bonding with 6 different fluoride ligands. So this fluoride ligands accepts donates electron, each fluoride electron it donates electron pair. That's why we are calling these are ligands. So interaction of these 6 filled orbitals of 6 ligands with sp3d2 hybridizable of iron 2, there are 6 bonds formation takes place. Due to this sp3d2 hybridization, this complex also exhibits octahedral geometry. So the shape of the complex is octahedral. In nature, it is a outer orbital complex. It is also known as high spin complex. Inner orbital complex we call as a low spin complex because of less number of unpaired electrons. Whereas outer orbital complex generally it has more number of unpaired electrons. That's why we call as high spin complexes. Okay. Due to this high spin, it is having, you see, 4 electrons, unpaired electrons in the d orbital. Due to these 4 electrons, it exhibits a paramagnetic behavior. It is also proved experimentally and theoretically. So this is the explanation of valency bond theory, application of valency bond theory to hexafluoridoferrate 2 ion. I repeat, hexafluoridoferrate 2 is exhibiting this type of shape. So this is an octahedral shape. Iron plus 2 is the central metal ion. It is exhibiting sp3d2 hybridization. It is the outer orbital complex or high spin complex. It is forming 6 coordination bonds with 6 fluoride ligands. It is accepting 6 electron pairs from 6 ligands, fluoride ligands. Since it is having unpaired electrons in 3d orbital, it is exhibiting paramagnetic behavior. So this is a explanation of valency bond theory to hexafluoridoferrate 2 ion. Okay. Next slide. Okay. So one more example. Hexaamino cobalt 3. See, we are studying valency bond theory with different examples. So far we discussed some tetrahedral, some square planar complexes. Now we are studying some examples for octahedral geometry. So one more example is, see, hexaamine cobalt 3. You see, this is a complex hexaamine cobalt 3 ion. The formula is this one. You see, this is a hexaamine cobalt 3. It is a cationic complex. In this complex, central metal ion is a cobalt in +3 state. So it is exhibiting 2 types of valencies. Primary valence is 3 and secondary valence is 6. We know that. So as per valency bond theory, central metal atom has to link, has to form coordination bond with 6 ligands. That means it has to provide 6 vacant orbitals for hybridization. Okay, we will see. One in the central metal atom is cobalt. Cobalt in 0 state is electronic configuration 4s2 3d. Cobalt is 27. Okay, 4s2 3d 7, 4p0 4d0. This is not 4d, it is a 4p. Okay, so 4s0 in cobalt 3 state, it is losing 3 electrons. 2 electrons from 4s and 1 electron from this one 3d. Okay, due to this losing of 3 electrons, it is exhibiting this type of electronic configuration. This one. Okay, this one 4s0, 4p0 and this one. Due to pairing is taking place here. This is a pairing is against Ohm's rule, but these electrons, due to the electron pairing, here we have two, we have, you see 2 d orbitals of 3d orbitals, 1 s orbital and 3 4p orbitals. So intermixing of this 4s1 4s orbital, 2 3d orbitals and 3 4p orbitals, we are getting 6 vacant orbitals. Mixing of these 6 orbitals, we are getting d2 sp3 hybridized 6 equal energetic orbitals. These orbitals are vacant. These orbitals, hybrid orbitals, accepts electrons from the 6 ligands. In this case, amine ligands, ammonia ligands, ammonia molecules. In ammonia and nitrogen has electron pair, which is capable of denoting this electron pair. So that's why it's acting as ligand. So this complex, this cobalt ion accepts 6 electrons from 6 ammonia ligands. That's why there are 6 electrons received from ligands. Is a dotted electron, dotted arrow marks is electron pairs received from ligands. That's why it is stable. It is exhibiting D2sp3 hybridization, what we call is inner orbital complex, we also known as a low spin complex. Further, we can say this compound is diamagnetic in nature. Why? Because it is having doesn't have at least one unpaired electron in the d orbitals. That's why it is diamagnetic. So this is the application of this theory to this hexaamino cobalt 3 ion. So shape of the compound is octahedral. At center of the octahedral is occupying cobalt 3 ion. It is linked to 6 ammonia ligands through coordination bonds. Since it is lacking an unpaired electron, it is diamagnetic in nature. This is the explanation of valency bond theory to this complex. Okay. Next. Okay, one more example. You see, what is this compound? You can easily name it. This is the complex. What is this cobalt ion is there? This cobalt ion is linking to 6 fluoride ligands. The formula is this. This is there here. So hexafluorido cobaltate 3. Why 8? This complex is having negative charge. That's why you have to put 8 as suffix. So minus 3 is there. Due to minus 3, cobalt has to exhibit plus 3 oxygen state. That's why name of the compound is hexafluorido cobaltate 3 ion. So in this complex, cobalt is in plus 3 state. Let us explain. In cobalt ground state, you know that cobalt in ground state 27, 4s2 3d7. This is the electronic configuration of ground state 4s2 3d7. It is exhibiting plus 3 state in this complex, but why it has to lose 2 electrons, 4s 2 electrons, 1 electron from this 3d. Due to losing these 3 electrons, it is the electronic configuration of cobalt 3 ion. This is 4s0, 4p0, 4d0 and 3d 6. Cobalt is 27 now, 1 electron lost from d orbital also. That's why pairing is doesn't happens in this case. That's why 1 s orbital, 3 4p orbitals, 2d orbitals. Intermixing of these 6 orbitals, there is a sp3d2 hybridization taking place. sp3d2. Due to this sp3d2 hybridization, we are getting a complex, octahedral complex. This is the shape of the complex. In this octahedral shape, the center cobalt plus 3 state cobalt ion is there. This cobalt ion is having 6 sp3d2 orbitals. The d orbitals is involving from 4d orbitals. That's why it is outer orbital complex. It's also known as a high spin complex. So due to this high spin availability of this unpaired electrons in that 3d orbital, it is exhibiting magnetic behavior. That is a paramagnetic property. So this is the explanation of valency bond theory for this complex hexafluorido cobaltate 3. So in this hexafluorido cobaltate 3, cobalt is center metal atom. It is exhibiting sp3d2 hybridization. It is a outer orbital complex or high spin complex. It is forming 6 bonds with 6 fluoride ligands. It is having a octahedral shape. It is paramagnetic in nature. So this is the explanation of valency bond theory about this what. Okay, finally, what are the limitations? We have some limitations. what this theory tried to explain geometry of so many complexes. Okay, but it is failed to explain some of the important points of coordination compounds. Let us explain. So many coordination compounds absorb visible region and exhibit color. That means valency bond theory doesn't explain color properties of different coordination compounds. So far we have discussed different tetrahedral, square planar and octahedral, but then never we discussed about the color nature, color property of a compound. So this is one of the drawbacks of this theory. Second one, some of the metal ions like copper plus 2 ions forms distorted octahedral numbers. So generally when we observe the shape of the copper 2 complex, it is not a regular octahedron. It is distorted. It's somehow it is disturbed shape. So why the structure of this octahedron is distorted, disturbed, elongated bonds? No reason for this elongated bonds in copper 2 complexes. So distorted octahedral structure is not explained by this theory. This is one of the important drawbacks. The theory cannot not explain the why some octahedral complexes are inner orbital complex and why are some are orbital. Just now we discussed same iron with chloride ligands, it is with chloride ligands it is outer orbital complex. The same iron plus 2 in cyanides, it is an inner orbital complex. Okay, why this is happening? Reason is not explained. It is telling it is due to inner orbital and outer orbital, but what is the reason? Same metal ion with different ligands, with the different complexes. That means multiplicity. That means high spin or low spin. Spin is differing. Due to this is not explained by our valency bond theory. So one more is valency bond theory is unable to predict whether the coordination complex formed by a metal ion with coordination number 4, either tetrahedral or square planar. So this is also one of the important. So nickel ion in some complexes is nickel plus 2 generally it exhibits 4 coordination number. With some ligands it is exhibiting tetrahedral. With some ligands it is exhibiting square planar. Just now we discussed nickel plus 2 with the chloride ligands it is a tetrahedral, whereas nickel plus 2 with the cyanide ligands it is a square planar. Why? Hybridization changing sp3 to dsp2. That's why, and the reason is not explained. Same metal, same oxygen state with different ligands, it is exhibiting different geometry, different hybridization. So that is not explained. That point is not explained here. This is one of the drawback. The same metal ion is bound to different kinds of ligands. They form coordination complexes with different stabilities. This theory could not explain the reason. So this is also one of the drawbacks. So same metal ion, different ligands. Okay, with these forming complexes, but the stability is changing. With some ligands, it is forming stable complex. In the same oxygen state, with different ligands, it is unstable. So stability is changing. The stability changing is not explained by the theory. So finally, measurement of paramagnetic moment is related to number of unpaired electrons. But some complexes magnetic moment is theoretically calculated based on the number of unpaired electrons. The theory could not explain the difference in theoretical and experimental determinants magnetic. That means the theory is predicting whether a compound is diamagnetic or paramagnetic, but it is not exactly sure why some compounds with more paramagnetic, compounds less paramagnetic. So values are also not exactly matching. So this is not explaining properly. Magnetic theory is not, magnetic properties are not explained properly. So these are the important drawbacks of this theory. So this is today's class. What we have discussed in this class, once again I recap fast. In this lecture we have discussed what in this class what we have discussed is valency bond theory, this application to square planar complexes and octahedral complexes, and finally what are the important drawbacks of this theory. What with this theory doesn't explain some of the properties of complexes, that is also explained. Thank you very much. We'll see you in the next class.